Welcome to this lecture on shallow neural networks. Shallow neural networks are built using artificial neurons. These networks typically consist of 2 or 3 hidden layers of neurons. Hidden layers are the layers that sit between the input and the output layers. And these networks are capable of learning any arbitrary input-output relationship. When you integrate these networks with automatic feature detectors, then we end up getting what we call as deep neural networks. And such neural networks have shown to perform at par with human beings. Before looking into shallow neural networks, let's take a look at a biological neuron that these networks try to model. A human brain has about 10 billion neurons, each connected to about 10,000 other neurons. Each neuron receives electrochemical inputs from other neurons at sites or locations that are known as dendrites. And when a neuron gets inputs whose sum together exceeds certain level, then it fires. And the firing consists of releasing an electrochemical impulse, and that impulse is carried to other connected neurons via fibers or connection links known as axons, as shown in the figure below. A model of the biological neuron was proposed way back in mid-40s by McCulloch and Pitts, and that is the artificial neuron model we are looking here. And this model consisted of number of input lines coming to a summing junction, and each input line was modulating the input through a weight known as the synaptic weight for that line. And the neuron was operating at an operating point that was controlled by the bias of the neuron. And what happened at the summing junction is that the summing junction looked at all the input values and basically multiplied each input value by its respective synaptic weight, added to that the bias multiplied by the bias weight, and produced a sum which simply we can call as a score or net, and that sum is basically nothing but a summation as given by this expression out here. And if this sum exceeded certain specified value, then the neuron fired and produced an output of 1. And if this sum did not exceed that specified value, the output was 0. And in this model, the threshold value or the cutoff value for neuron to fire was taken as 0, which means if the sum was positive, the neuron fired. If the sum was negative, the neuron did not fire. So in this slide, I'm just showing you few numbers on the input side, and then we have some weight values here. So based on those numbers and weight values, we get some output, and basically in this case the output will be 0 for the given set of values. So that's how really a very simple artificial neuron works. Pretty simple model. The original model used unipolar threshold nonlinearity, which is also known as sine function, as an activation function. So basically, as we saw, for the original model, the output was going to be 1 if net sum was greater than 0, and output was going to be 0 if net sum was less than 0. Later on, people started using another nonlinearity, which is known as the sigmoidal function or sigmoidal nonlinearity. And in this case, the output is expressed through a formula which is nothing but the formula for a sigmoid function, and the formula is 1 divided by 1 plus e to the power minus net. So with sigmoidal nonlinearity, you have the output which lies in the range of 0 to 1, and you get continuous values in the range of 0 to 1, unlike the original unipolar threshold nonlinearity where only two output values were possible, 0 or 1. The sigmoid function was very popular in 80s, but it's not that popular in deep learning nowadays. And the reason is that this function saturates as the net value increases on the positive side or on the negative side. And also the output range 0 to 1 seems to create issues in terms of learning if you're going to have many layers in your network. The another name for sigmoid function, of course, we should all know or remember, is logistic function, and we have covered that in our earlier lectures. Instead of having unipolar activation functions, one can also go for bipolar activation functions. So instead of having a unipolar threshold nonlinearity, we can have a bipolar threshold nonlinearity, which is known as a signum function. And in this case, the output is 1 if the net is positive, and the output is minus 1 if the net is negative. Corresponding to sigmoid function, we can also have a bipolar continuous function here, which is known as the hyperbolic tangent function. And again, this function approaches plus 1 or minus 1 in the limits. And the expression for this function is 1 minus e to the power minus net divided by 1 plus e to the power minus net. Like the sigmoid neuron, the activation in hyperbolic tangent function also saturates. However, unlike the sigmoid neuron, the output in this case is zero-centered, so it kind of gives better performance compared to the sigmoidal nonlinearity when you have more number of layers. Yet another activation function is what we call as a rectified linear unit function or ReLU function. This function behaves as a linear function if the net value is positive, and if the net value is negative, then the output of this function is 0, as shown in this slide here. This function has become popular in deep learning. Empirical results have shown that using this function, one can train the networks 5 to 6 times faster. Computationally also, this function is much simpler. There is one drawback with this function, and that is this function can cause some of the neurons in a network to end up as dead units. That is, their output becomes 0 because the gradient cannot drive that output anymore one way or the other, because that unit is operating in this particular part of the curve. So what happens is that if you want to avoid this issue, you need to pay a lot more attention to the learning rate that you want to use. There is a variation on ReLU, and that variation is known as the leaky ReLU. And the basic idea behind this variation is to avoid the issue of dead units. So instead of function being 0 for all negative values, what we have is a small negative slope, so that there is some movement, some activity there when the net value is negative. This seems to have shown promising results, but the performance with this activation function doesn't seem to be very consistent. That means sometimes people are getting good results, sometimes they are not able to get good results. So it's not that popular, and ReLU remains the most popular activation function. Now let's look at a linear neuron. Of course, in the linear neuron, the activation function is a linear function. So the model for a linear neuron is shown here, and you can think about this model and see whether this model really reminds you of something that we have looked at earlier. Especially if you look at our very first lecture on regression or linear model for regression, you will find that this model is exactly same as that linear regression model. So a linear neuron in some sense is doing linear regression. So the expression for modeling this can be again very similar to what we have seen earlier. So through few steps you can say, all right, this model can be trained using this formula which we have seen earlier. Now one might say, all right, with the linear neurons, can we form a network where we have several layers? You can think about it, but the answer is that when you have a linear neuron, or when you have linearities and you take two linear blocks and put them in cascade one after the other, you don't really achieve any additional strength or any additional capability in your model, because two linear functions can be always combined to yield a single linear function. So this model is okay for starting to study, but not very useful other than doing linear regression if you want to use this model. There is using the threshold nonlinearity that was proposed in the original model. If you put that nonlinearity as your activation function, then the resulting model is also known as a linear threshold unit, or LTU. This model is also known as the perceptron. And if you remember our discussion on linear classifiers, basically we talked about perceptron at that time. So essentially this model is behaving as a linear classifier, and the output is going to be 1 if this inequality is satisfied, and output is going to be -1 if this inequality is satisfied. Of course, this is +1 and -1 assuming you are using a bipolar nonlinearity or bipolar step function. If you were using it unipolar, then it will be 1 and 0. And again, one can train this model, or one can find the parameters of this model using the updating rule that is shown here, W new equal to W old plus alpha times. For all misclassified examples, take the sum of yi xi. That is the perceptron learning rule we had seen earlier, and again you can do the implementation in the batch mode or in the incremental mode. Let me summarize the steps of perceptron learning rule. Instead of a formula, let me just summarize it in terms of bullet points. So perceptron learning rule uses training data from two classes. The training vectors are augmented by an additional component with value 1. This is, as you might remember, is needed to include the bias term in the calculations. The weight vectors are initialized randomly. And if we present training examples one at a time, what we do is we present the example and compute the output of the perceptron. If the output matches with the desired output, that is, if the example is from class 1 or positive class and the output is positive, we don't change the weight vector, leave the weight vector unchanged, and we move to the next example. If the output is not correct, that is, the model is making an error in terms of classification, the weight vector is modified either by adding to it or by subtracting from it the current training vector. And we move to the next example. And what we do is, as we go over the examples, we shuffle them and continue repeating over and over again till we come to a situation where perceptron produces correct output for all examples. Now let's look at what kind of decision boundaries produced by a perceptron. As we had seen earlier, when we talked about binary classifiers, the perceptron is going to be producing a linear boundary. You can say it in 2 dimensions. The boundary is a line, and on one side of the line we have what we call as the positive region, where the wi xi over all i's is greater than 0, and on the other side of the line is the negative region, where the net sum is negative. Let's take a very simple example showing how perceptron learning works. So suppose we have 4 examples in 2 dimensions. The positive examples are A and B, and negative examples are C and D. And their corresponding feature values are shown here. The first thing we need to do is to add the bias term. So if we add the bias term, all the examples become, so A becomes 1, 1, 1, B is 1, 2, 3, C is 1, 3, 1, and D is 1, 4, 2. Let's say that our initial weight vector choice is 1, 1, 1. So what we do is we take example A and present it to our network. That means we calculate the dot product between our weight vector W0 and A. And in this case, the answer is 3, which is positive. So the network or our model or our perceptron unit produces an output of 1 or positive output, which matches with the class of A. So no mistake. So we move on to example B. For B, the output is 6. Again, it is fine, no problem. So we move on to example C. For C, the model is giving us a value of 5. We expect the model to produce a negative output here. That means this example is being misclassified. So we do the correction to the weight vector. And that correction is done by subtracting C from our current weight vector. The idea of subtracting C here is that when you do that, basically you are going to be pushing the dot product with the updated vector towards 0. That is, its value is going to go down from the earlier value, which means chances are it might cross over from 0 and become negative, and that is what you really want. So our corrected weight vector or updated weight vector becomes now 0, minus 2, 0. Now we bring in the example D and we do the calculations. So in this case, the net value is minus 8, which is fine because that is what is expected in negative value. Now we go back and look at example A again because we made some changes to the weight vector. So we want to make sure that it works for A. So when we do the calculation, we find that the net value now is -2. That means it's not okay. So we apply the correction. And correction that is being applied here is simply adding A to the weight vector. So when we do that, in this case, we are pushing the weight value in a direction so that after correction, it will produce an answer which is going to be much more than the answer it was producing earlier. That means hopefully it will drive for A the answer to the positive side. That is what we want. So in this case, the updated value becomes now 1 minus 1, 1. So we bring in now value example B and do the net calculation, and we find that net value is 2, which means it's okay. Then now we bring in C. Again, we find that in this case, the response is fine. We bring D. We find the response is fine. We go back and bring A again, and we find that response is fine. That means the current weight value is producing correct response for A, B, C, and D for all our 4 training examples. So we can say that at this point, we have a model that has learned to distinguish between AB and CD, and we have the proper set of weight values. So these weight values are what we call as a solution to our model. And you can note here that if the examples are linearly separable, this process will keep on going, and at some point it will terminate, as it terminated in this particular case. On the other hand, if the examples are not linearly separable, then learning will not cease, because there will always be some mistakes and there will always be some corrections, and this process will keep on going. Okay, now not all problems are linearly separable problems, so let us consider what happens when the examples are not linearly separable. I want to mention here that you never know whether a given training set is a linearly separable problem or it's a non-linearly separable problem. Only in 2 dimensions you can find out by looking at the data whether you can draw a line to separate or not. But once you're working with real problems with 10 or 20 or 50 dimensions, there is no way you can figure out whether something is linearly separable or not. So in such cases, you have 2 possible options. One is to use layers of perceptrons, as I show you in next few slides, or modify the criterion for optimization so that instead of doing an error correction procedure, which is what Perceptron does, we follow what we call as an error minimization procedure. So we are going to be looking at that also later on. So let's look at an example which uses layers of perceptrons to solve a problem that is not linearly separable problem. So in this case, we are looking at an example which consists of 4 training samples, 2 from class A and 2 from class B. And the data in this case is purely binary data. So if you look at this data, you can see that points from class A cannot be separated by a line from points from class B. So here is a problem which is not linearly separable. While looking at the data, we can also realize this, that we can draw 2 lines such that points from A and B are separated in a way where the points from class B lie outside these 2 lines and points from class A lie within these 2 lines. So if you look at the arrangement of these 2 lines that I showed you in the previous slide, you can look at this arrangement in this particular fashion. You can think of a step 1 where we use two perceptrons which map our input data into some intermediate representation. And then we operate on this intermediate representation to perform the classification. So the table here shows you x1, x2 as original raw data or raw features, and y1 and y2 as intermediate representations for our examples from A and B. And then in the second stage, we can see how we can easily separate y1 and y2 using a single perceptron. So if you look at this table or this idea of layer of perceptrons, this can be represented in the form of a picture like this. So x1 and x2 are two signals coming in, and these signals go to two perceptrons which form what we call as a hidden layer. And these two perceptrons respectively produce their outputs. And those outputs, if we combine them through another perceptron, which is out here, then you can see that we can easily separate points from class A and points from class B with this architecture or with this arrangement. So this idea of having multiple layers of perceptrons can be extended to not only to 2 layers, but you can go into 3 layers or 4 layers and so on. Okay, let's look at another example. In this case, what we can do is we can have 2 sets of 5 perceptrons or 2 sets of 5 neurons produce 2 yellow regions. And then we can combine these 2 yellow regions through another perceptron to produce a final boundary that is going to look like as shown over here. So you can see this is a fairly complex boundary, and we can get this boundary using the arrangement of perceptrons as shown on the right hand side. Although I haven't shown you the actual weight values that you will need, but those weight values can be easily figured out once you know the location of how the boundary is sitting in x1, x2 plane. So the basic idea from these 2 examples is that one can get any arbitrary arrangement or any arbitrary boundary or any arbitrary mapping between the input and output, provided you are willing to arrange number of perceptrons in number of layers. So there is actually a very important mathematical result which says that neural networks are universal approximators. That is, with a single hidden layer of neurons, it has been shown mathematically that any arbitrary input-output mapping is possible. So basically, if we want to deal with nonlinear problems, all we need to do is to have multiple layers of neurons or a feed-forward network or a network that we call as multiple layer network. So before moving on, let's go back to what we call as a sigmoidal neuron. The reason we want to talk about sigmoidal neuron is that if you are going to arrange multiple layers of networks, perceptron model where the activation function is a threshold or a step function kind of nonlinearity is not going to work. And the reason is very obvious. That is, for a multiple layers of perceptrons, you will be needing some kind of optimization to find the weight values, and to do the optimization you will be taking partial derivatives, and to take those partial derivatives you need activation functions that are continuous in nature. So let's get back and look at what we call as a sigmoidal activation function for a neuron or a sigmoidal neuron. So in this case, the output y hat can be expressed as 1 divided by 1 plus e to the power minus w transpose x, where w transpose x basically represents the net or net sum value produced by the neuron. So in this case, let us define a loss function. And what we'll do is we will define a loss function by comparing the actual output, that is the output after the activation function, sigmoidal function, with the target or the desired output. So the expression is going to look very similar to the MSE loss function, except that in this case the output that we are taking is coming at the end of sigmoidal function. So our loss function can be expressed JW as shown, and one can then calculate the gradient as shown. Now, since we are using sigmoidal function, so if you look at the derivation for the gradient, we have to take the derivative of the exponential function. So here is the derivative for the exponential function. So let's define f of z as 1 divided by 1 plus e to the power minus z. And then f prime z is nothing but the partial derivative of function f with respect to z. And if you apply the basic calculus and do a little bit of manipulation, you will find that f dash z is really nothing but output times 1 minus output. So that's a nice way of remembering how the derivative of the sigmoidal function looks like. So getting back to our sigmoidal neuron, y hat is given as shown. So if we were to take the del y hat by del w, that is what we are going to get. We are going to get it as yi hat times 1 minus yi hat times xi. Thus, for a single input example, we can write our learning rule as equal to del z by del w. That is, the weight adjustment rule is given by yi minus y hat times y hat times 1 minus yi hat times xi. Or if you want to express it in terms of actual and target output, you can say yi is the target output, yi hat is the actual output. So target minus actual times target times actual times 1 minus actual times input. So that's the formula, pretty easy to remember for weight change when you are using a sigmoidal activation function. So basically, if you look at expression for del z by del w, this is how it looks like. So the first term yi minus yi hat, you can call it as an error because that's the difference between desired or target minus actual. So that's the error times output times 1 minus output times input, or error times actual times 1 minus actual times input. So you can express the weight change for the ith training example, that is the jth component of the weight change for the ith training example, delta w j is given as minus error times output times 1 minus output times xij, and negative sign is there because we want to decrease the error. Now the highlighted part of the formula is going to be different if we are going to be using different activation function. For example, if you go for hyperbolic tangent function, then partial derivative of hyperbolic tangent function is different and the formula will change. In any case, this rule, delta W change rule, is known as generalized delta rule. The loss function that I used in the earlier slides was mean square error loss functions. We have seen earlier cross entropy loss function, which is pretty popular loss function and very useful. So this is another loss function that we can use. And in this case, yi is the target or the desired as before, and yi hat is the actual for the training example. And if you recall your formula for the cross entropy loss, that formula is given by as shown on this slide. So if you were to minimize the cross entropy loss function, so let's take del J by del W. So if you carry out the derivatives following the basic calculus, you will find that upon some simplification, we end up with a rule which tells us that the updated weight value or new weight value will be W old plus alpha times target output minus actual output times xi. Again, this is a formula that we have seen earlier, so pretty familiar formula. Now let's go to multiple layer neural networks. So let's say that instead of just having a single neuron with whether sigmoidal activation function or hyperbolic tangent activation function, let us have a network of neurons such that we have one or more layers of neurons. So the architecture that we will be discussing here is as shown here. So you have what we call as the input layer, then you have what we call as the hidden layer, and that is the output layer. So the neurons in the hidden layer are called hidden units or hidden layer neurons. And in the output unit, you might have one neuron or you might have multiple